Hello, everyone. It is with pleasure I introduce Dr. Lawrence Krauss. Dr. Krauss is the Foundation Professor of the School of Earth and Space Exploration at Arizona State University. He has made significant contributions in cosmology, where he was one of the first physicists to suggest the existence of dark energy, a substance which may be responsible for 68.3% of all the total energy in the observable universe. Dr. Krauss is also a tireless advocate for public understanding of science. He served on the Science Policy Committee for Barack Obama's 2008 presidential campaign, contributed articles to The Atlantic, The New Yorker, and Newsweek, and written several New York Times best-selling books on science, including his previous book, the well-noted and well-regarded Universe from Nothing. My first exposure to Dr. Krauss's work came with one of his early books, The Physics of Star Trek, which I found enthralling for its thorough and altogether serious look at the physics, plausible and otherwise, of one of my favorite series. As a brief aside, Dr. Krauss, I feel like there was a missed opportunity. You wrote a follow-up called Beyond Star Trek, and I feel it should have been named The Physics of Star Trek 2, The Wrath of Krauss.
You're taking that out of my, I put that in my appendix.
Oh, you did?
Yeah, exactly.
Oh, you did now.
Okay.
Today, Dr. Krauss is here to talk about his latest book, documenting our current understanding of nature, the history of one of humanity's greatest scientific achievements, the Standard Model of particle physics, and its implications for our existence, and what promises to be the greatest story ever told so far. Join me in giving a warm welcome to Dr. Krauss.
Thank you. Thank you. Thank you. Thanks. Well, it's a pleasure to be here and see all of you. And I understand it's lunchtime, so I shouldn't go overtime. So I'll make a shorter version than normal because I know you have really important work to do. So, in any case, the quote that I had here along with the music comes from a book that actually a friend of mine who's a filmmaker named Werner Herzog recommended to me, and he, you might have seen his most recent, well, not most recent movie, but second most recent movie, Lo and Behold, which is about the internet, which is nice. So there's another one that just came out, which is a fiction called Salt and Fire that I'm also in as a villain, but it's a weirder movie. But anyway, this book, which is called The Peregrine, is about a peregrine, and but it is a wonderful naturalist book if you ever want to read it. But the quote is what's particularly important, which is the hardest thing of all to see is what is really there, and that's really the thrust of the content of my book, which is that the world we live in is an illusion, and it's been an amazing story for particle physics and oh, look at that. Okay, is there a reason that went off? Auto power off engaged. Auto power off was engaged. So, waiting for projectors to start. Good. I'm very impressed with the technology. So, anyway, the Standard Model of particle physics, and in fact particle physics in general, has been about trying to understand the fundamental structure of matter and energy. And it is really an amazing story of how different the universe is at fundamental scales than the scale we see. And one of the real implications, and one of the reasons the subtitle of the book is called Why Are We Here, is that the universe that we exist in is an accident in a well-defined way, which I'll talk about until the projector gets to there. Let me just get to the slide I want to do so when the projector actually turns on, which is certainly not now. Light just came on. That's good. We can get to the image I want to show, which is of a window in the wintertime with ice crystals on it. I was actually just in Phoenix where I teach, and I gave a lecture on this, and I had to explain to people those were ice crystals. But here we go. And so these are beautiful. But what I want you to do is think for a second of what it would be like if you lived on one of them. So I say this one, okay? If you evolved on, and we can still use that word in the U.S. If you evolved on that crystal, what would happen? Well, the physicists, I don't know where it is in that one, but anyway, let's say with this one. Oh, no, there it is. The physicists working in this world would say, well, okay, I can work out the forces. The forces along the spine of the crystal are very different than the forces perpendicular. So they'd come up with laws of physics which would explain and predict how things moved, and there'd be one set of forces in this direction and forces in the other direction, and that would seem natural. There'd be theologians who'd say, explain why God ordained that direction to be the proper direction for life. and there'd be wars fought over whether that was the right direction or that was the right direction to pray to. And all of that would have significance, which of course is completely illusory. That it is just an accident, and the crystal can point in any given direction. And but it wouldn't seem that way if you lived on that crystal. And that's essentially the world we live in. All of the facets of the world that make it look like the universe is designed for our existence are pure accidents in a fundamental way, which I'll try and describe. And we, of course, the world looks like it's designed for us, but at a fundamental level, it's actually antithetical to our existence, as I'll describe to you. Now, the story's long and winding, and obviously I said I want to give an abridged version so you can get back to work. But so I'll start fairly late into this. But the story actually begins 2,000 years ago with Plato and then works through Maxwell and Einstein, talking about the major revolutions that have changed our perspective of our place in the universe. And one of the things that describes pretty well the progress of science, certainly in physics in any case, is when we know we've made progress when two things that seem very different on the surface are seen to be different reflections of the same thing. And then we know we've made progress. And that pretty well characterizes almost all the progress in physics over the ages. From, for example, in recent times, the recognition that electricity and magnetism, which seem so different, are really exactly the same thing. And one person's electricity is another person's magnetism. That led to the realization that space and time, which seem different, are really the same thing. And what one person sees as space, another person will measure as time. We live in a four-dimensional universe, not a three-dimensional universe. And those kind of developments have progressively told us that the universe that we see is kind of myopic, because we perceive these three-dimensional slices of a four-dimensional universe, which is why it seems so non-intuitive to us that the universe is four-dimensional. And when I'm running with respect to you, I'm seeing a different three-dimensional slice of a four-dimensional universe, which is why things seem strange and relativity does what it does. And I talk about those things at great length in the book. So though up to that point we developed a theory of electromagnetism and a theory of gravity, and all seemed well until we got to a later stage. And I want to begin the later stage with this guy who all of you know, I assume. It's Richard Feynman. And who was probably, was one of the greatest physicists of the second half of the 20th century. And what he won the Nobel Prize for with others was the recognition that, of course, at the fundamental level, the world is quantum mechanical. And if we want to have a theory of electromagnetism, we need to put it in accord with quantum mechanics. And the theory they developed, called quantum electrodynamics, is a theory that merges electromagnetism and quantum mechanics. And he presented a way of thinking about this to understand the electric force between two charges, which had been understood by Faraday and Maxwell, in a slightly different way, a way we talk of by Feynman diagrams, as we call them. But it's particularly interesting. So this is an electron, and it repels another electron. And it does so by the exchange of a particle, a photon, the quantum of the electromagnetic field. The electromagnetic waves come in particles, and photons are the individual quanta. Now, what Feynman used in developing this is a key aspect of quantum mechanics, which is central to quantum mechanics, which is really the same thing that's used in Washington and corporate America, which are now the same thing. If you can't see it, anything goes. Okay? That's basically it. And we'll learn more about that with investigations over the next year, I certainly hope. But so the idea is that this electron emits this particle, this photon of light, but that's impossible. It's not allowed. An electron just sitting there cannot emit a particle of light, because where did the energy come from? If the photon carries energy, where did the energy come from? The electron is still there. If it's an isolated electron, it can't emit a photon because that doesn't conserve energy. But that's okay. That's allowed by the Heisenberg uncertainty principle, which is responsible for that Washington rule I gave you. The Heisenberg uncertainty principle says if I measure a system for a short time, then I can't know its energy exactly. There's some uncertainty in the energy. So if I emit this photon and it violates energy conservation, that's allowed in quantum mechanics, as long as the photon disappears in such a short time that I can't measure it. It's just exactly like embezzlement. Okay? I'm sure Google does this every day at some level. Because if you get the money, and as long as you put it back before anyone notices, you can do whatever you want with it, right? And that's